Thank you. I'm Kang Namwoo, CEO of Narnia Labs and a professor at KAIST. Today, I'd like to talk about the somewhat weighty topic of the future of autonomous design, from generative AI to agentic AI. Let me introduce myself briefly. I currently lead the Smart Design Lab at KAIST. I have about 20 master's and doctoral degrees. After diligently researching with students, I decided to use this well-developed technology to positively impact industry, and so I founded a startup called Narnia Labs. Currently, we have 30 members with a total of 50 people working on product design research based on generative AI for over 10 years. So, what I want to share today is as follows. Let's first talk about why artificial intelligence, or AI, is needed in engineering design, and especially why it's needed in Korea. In fact, an alliance called Manufacturing AX Max was launched in September. Hosted by the Ministry of Trade, Industry and Energy and the Korea Chamber of Commerce and Industry, this alliance aims to drive innovation and fundamentally transform manufacturing with AI by the year 2030. Over 1,000 companies, research institutes, and schools have come together under the goal of creating 100 trillion won in value. This alliance is largely divided into 10 branches, one of which is the AI Manufacturing Service Alliance, which provides services that can increase the added value of the entire manufacturing industry. Therefore, the convergence or standards of design, product development, and manufacturing are key areas. The place that is doing it is now the Manufacturing AI Manufacturing Service Alliance, and I am honored to be the chairman. So if you think about why South Korea is trying to innovate manufacturing AI, in fact, even 10 or 15 years ago, we used to say that software was taking over the entire world. This is because big tech companies centered around Silicon Valley in the United States were taking over all industries. It was a time of disruption and innovation. These days, we talk differently. Manufacture is now eating the world. Why all of a sudden? Isn't manufacturing a thing of the past? Why is that? And even then, the center isn't the US, but China, because China was good at manufacturing, and now it's also good at AI, so it's eating up industries around the world, centered around physical AI. It is. It's changing. As you all know, manufacturing accounts for over 24% of our country's GDP. Even now, if you look at the rankings, we're in the top 10 globally. In fact, since the percentages are almost identical, it's safe to say we're tied for 6th or 7th. Our country is still heavily reliant on manufacturing, but you're seeing the problem in all industries, right? With population decline and a shrinking young workforce, there are hiring issues, hiring experts, and falling behind China in terms of price competitiveness. We're bound to fall behind in the competition for scale. So AI isn't the answer. It's not the only answer, but no other solution seems to be working. So we're now focusing on AI in manufacturing. I feel that innovation is not just an option, but truly a necessity. When we talk about manufacturing, many people tend to think only of production, but in reality, manufacturing actually covers the entire product life cycle. Innovation is a necessity. Manufacturing is more than production. It covers the whole product life cycle: planning, design, building, testing, production, distribution, management, after-sales service, and delivery. There are so many different specialized fields connected, including recycling. If we make a table with added value for these fields, there is something called a smile cup. It looks like a person smiling. So when we look at it from the production perspective, the pre-production and post-production stages have high added value. So in fact, we are jumping into the world. There are a lot of companies at both ends, so the pre-production stage, the pre-production stage, the pre-production stage. There are many companies that have made progress at both ends. So in the pre-production stage, before manufacturing, before production, major work such as product development, R&D, design, branding, etc. takes place. That means ultimately, if we innovate high value added areas with AI and achieve AX, the effect will be great. From our perspective, from our country's perspective, that's why we focus on product development. I'm saying that we can only truly see meaningful results if we actively innovate and improve that process with the help of advanced AI technologies. Of course, all areas and aspects are important and deserve attention. Oh yes, I completely agree that AI is necessary for product development and design in Korea, especially as the industry evolves. Let's think about how engineering design is changing with AI from a broader and more comprehensive perspective. Here's my perspective on this important topic. I've been practicing optimal design for decades. Optimal design. My advisor was someone who spent his entire life practicing optimal design, and I learned from him. So, in a way, the most utilized optimal design is simulation-based optimal design. You all have many great CAX tools, CAD, CAM, CA, etc. So, by using those computer-aided tools, people can do it faster and more efficiently. It was a time when we were developing products and we could optimize them. However, we have been working hard at Namwoo Labs and KAIST to transition from optimal design to generative design. Generative design. Generative design attempts to change the paradigm of existing design by using generative AI technology as its core. So now we have another great resource called AI for humans, but it's still not that great. Decision makers are people. Even though better tools have been developed, decision makers are still people. There is still a long way to go. There is still a long way to go in the industrial field. Decision makers are humans. So while better tools have emerged, decision makers are still humans. We still have a long way to go. General AI isn't widely deployed in industrial settings yet. There's still much work to be done, and we'll focus on it, but we must continue to look toward the distant future. Then I believe the next era will be the era of autonomous design, or what we call agentic AI. I'll share my opinion on the differences between generative AI and artificial AI later. The key difference is that the design maker is no longer a human, it's AI. The era of AI using AI to design is coming. While people have been focusing on designing using AI, the era of AI using AI to create good designs will come. Of course, people will also be involved. Ultimately, it will likely be AI that performs evaluations and oversees. But it seems likely that many roles will be assigned to AI. So, within this larger picture, I'll first show you the efforts that Namwoo Labs and KAIST have made in transitioning from optimal design to generative design, and then explain how we define the problem. When we say simulation-based optimal design, the following process is followed. Defining the problem means when we talk about optimal design or simulation-based optimal design, the process is as follows. First, we define the problem. Defining the problem means defining the objective function, design constraints, and constraints. Then, in the case of shapes, defining design variables means parameterization. So, after defining the shape with a small number of parameters, we change them and run a C simulation. We gather that data, use machine learning techniques to create predictive models and swarm models, and then use an optimizer to find the optimal values based on those models. We've been doing this consistently for a while now. However, this approach has one fundamental problem. First, the designs we're trying to create often can't be parameterized. This is because the geometry is so complex that it can't be expressed from x1 to x10. Current machine learning techniques typically, because the dimensions of input and output can be substantial, right? Secondly, even if I could express the design I want with many design variables, I couldn't create a surrogate game model for it. Existing machine learning techniques can't structurally increase the dimensions of inputs and outputs. Finally, even if I made such a function or a surrogate game model, that surrogate game wouldn't be possible. When models are highly nonlinear and complex, finding the optimal solution is hard. So, the main limitation of traditional simulation-based optimal design is that real-world industrial design problems are extremely high-dimensional. So when we ask if AI can solve these problems, deep learning, by AI, I mean deep learning, is the most prominent. The greatest advantage of deep learning is its ability to solve these problems. It can compress a high-dimensional X space into a low-dimensional Z space. This is the ability to represent something that would require thousands of dimensions using just tens of dimensions. This ability serves to perform feature extraction or dimensionality reduction, which reduces the number of dimensions. So what does this enable? Since it can extract features on its own, you don't have to parameterize complex shapes. It can independently identify key features and use them as input to create a surrogate model. This means you don't have to do parameterization. Second, as I mentioned, since dimensionality reduction is possible, for instance, while it's difficult to perform optimal design in 1,000 or 2,000 dimensions, it becomes much more efficient to do so by reducing it to 10 or 20 dimensions. And that low dimensional space is also well suited for generating new things. So from that perspective, this single page essentially contains the theoretical framework for performing generative AI-driven design optimization. So there are three main modules: generative AI, predictive AI, and optimization AI. So first, let's look at the meanings of X, Y, and Z. X represents the design, Y represents the engineering performance, and Z represents the compressed space. It's the space that deep learning has compressed X into. So what is generative AI? That's number one. It's essentially the mapping from Z, the compressed space, to X, the actual design space. If you train this mapping based on data, you can later change Z to generate a new X. And below that, predictive AI, number two, refers to the mapping from the X space, or design space, to the engineering performance, Y space. This allows you to obtain the function Y equals F of X. So ultimately, when you have both this generative AI and predictive AI, optimization becomes possible. And there are two ways to do this. On the left, the iterative optimization method is similar to existing surrogate model-based optimal design. However, the optimization is performed in the Z space. You change Z to create X, use that X to predict Y, and then continue searching for a good Z. Then, once you find the best Z in the low-dimensional space, you map it to X in the high-dimensional space to create the final design. The second method is to make the generative model conditional. So while you're still creating X from Z, you also input the desired engineering performance, Y. This is like telling the model, find a design that satisfies this engineering performance, or optimize for it, or generate it. So to summarize the key idea in a single sentence, the advantage of performing optimal design with generative AI is that you can do it in the reduced dimensional space. All right, so, well, there won't be any more mathematical formulas from now on, so you can relax and just watch. AI is now multimodal, so 3D data, 2D data, and 1D data can be input in any combination, and 3D, 2D, and 1D results can be output in any combination. So the data you typically use for design can all be represented this way. 3D would be, say, CAD, and 2D could be an image from a specific view. Design, or it could be an image from a specific view. And 1D typically represents all numerical values that can be expressed in Excel, like material properties, all those kinds of values. And the outputs could be values from CAE analysis or results from testing. Thinking along these lines, by combining these different modalities, we can categorize the common problems we're trying to solve. It's like creating a menu, in a sense. So we have 3D generation, 3D prediction, 3D optimization, then 2D generation, 2D prediction, 2D optimization, and 1D prediction, 1D optimization, and so on. Based on our experience, we've defined these problems. First, let's consider a 3D design scenario. For 3D prediction, as you can see at the top, when we think about making a prediction, after the AI model has finished training, we provide it with a 3D CAD as input. Along with that, we provide the boundary conditions as 1D data. The AI will then predict the results of a KAI or a test. And when it predicts, it can predict 3D field values, or it can predict 1D scalar values. A 1D scalar would typically be a maximum value, or global stiffness, or something similar, while a 3D field value would represent all the nodal values. Furthermore, the prediction can be divided into static or dynamic. Are we trying to predict a value at a specific point in time? Or are we trying to make a transient prediction as a time series? You need to use the optimal models that are appropriate for each case. Once the prediction is made, we can then move on to generation. For generation, as you see below, we provide conditions to the generative model, the design requirements we want, and it generates a corresponding X. So ultimately, since we have both a predictive model and a generative model, we can connect the two. So you can generate, then predict, then generate again, and predict again. Or you could even embed the prediction within the generation process. So you can generate while predicting. This way you can find an optimized 3D design. This is, in a sense, a very abstract representation of the process. Now, let me show you a real example. As a case study, this is a design for a molded KAIST circuit breaker. From a 3D generation perspective, we start by non-parametrically generating various cases without parameterization. And for parts we want to change in detail, we can also apply deformation. This allows us to create a variety of CAD models. We then train a deep learning model on the analysis results of these CADs to predict structural performance or outcomes like injection molding. Now that we have a generative and a predictive model, we can optimize as mentioned earlier. This lets us find the Pareto front, which is good structurally and for productivity. We can also rank each design alternative. However, some of you might be thinking, well, there are so many open source options these days. Can't I just grab some code from GitHub, train it on my data, and get a decent result? Yes, well, that might be possible. It could be. But here's the problem. In this particular study, the data we received from the company consisted of just 28 shape data samples. We need to learn 28 pieces of shape data, and the 3D generation research in computer science, as described in the paper, relies on enormous amounts of data. And that data isn't our manufacturing data, but rather the small, bulky shapes typically used in the metaverse or games. The data we're trying to learn is always sharp, thin, and detailed, and it's a completely different domain altogether. So when you think about it with a model learned in a different field, the expression open source comes out like that. Of course, I can't use it. So if we do a very good and thorough job of pre-processing and optimizing the data to best fit the specific characteristics of our data, it really starts to take shape a little bit. Still, it's not enough. Then we choose the one that best suits our manufacturing data. We must tailor and optimize our data and model for manufacturing. We need to create it, and then things get a little better, but it's still not enough. So purely data-driven design still has its limitations. So we mobilize all of our existing design technologies, rule-based post-processing and pre-processing technologies, and combine them with data-driven design. Now we can start to create somewhat more realistic shapes. Therefore, if we try to use AR for product design in our manufacturing industry, it requires a tremendous amount of trial and error and know-how. I wanted to take a moment to tell you this. In this particular case, we have now incorporated this 3D design into our CAD system as an API, which is an application programming interface. This is a case of collaboration with Siemens Korea. For example, when designing a duct for a refrigerator, we input some specific engineering performance targets. Then, when we hold a summit or meeting, I start by creating ducts behind the refrigerator, which is necessary to ensure proper airflow and help the appliance operate efficiently. In your approach, you created these ducts parametrically, meaning you used adjustable parameters to define their size and properties, making it easier to modify them later if needed. However, in this case, you did not actually parameterize the ducts, so they were made with fixed dimensions, which can make future changes more difficult. After I finish creating the ducts, I download the resulting files to my computer. Once the download is complete, I upload these files to the server, which helps keep the project organized and ensures the designs are safely stored in a central location for future reference or collaboration. I'll try it on my fridge, I'll stick it on to check its performance, and check for any differences with the original design. This was an example of how a trained AI model can be seamlessly integrated into an existing design process and workflow. So now that I've discussed 3D, let's move on to 2D. The concept is identical. The concept is the same, but you might ask, why not just use 3D? Why use 2D? Well, since 3D is so complex, we're essentially reducing the problem to make it easier to solve. So often a 3D CAD model can be adequately represented as a 2D depth map. In those cases, you don't necessarily need to keep the 3D data. You can just have it as a 2D depth map, or for many designs that have a uniform thickness, you may only need the cross-sectional information, right? In that case, you can just work with the cross-sectional design. Using these representations, we can create a predictive model in the same way, just as we did with 3D. Now, for the generative model, directly generating in 3D is quite difficult due to data issues and the models becoming very heavy. But the advantage with 2D is that there are so many foundation models. With so many foundation models available, we can leverage them very effectively. So it's often more effective to first create a 2D depth map or image, and then reconstruct the 3D model from that 2D data. This approach works very well. By doing that, you ultimately perform the design optimization in 2D and then create the 3D model from it. Now for an example, and there are many we could use, but if we just show one, let's take the case of a wheel. When we create a photorealistic wheel image like this, we're not just making an image that looks plausible. Instead, we predict the performance that would result from its 3D implementation. We consider factors like its stiffness and mass, and then create an optimized 2D image that meets those criteria. This is done by considering all the 3D properties. Then using that image, we reconstruct it in 3D. After finding the optimized design, we use that design to reconstruct the 3D model. So for a problem that's difficult to solve directly in 3D, we temporarily move to 2D to solve it and then come back to 3D. Now we're left with 1D. We've done 3D and 2D, so now it's 1D's turn. Now for 1D, generation is actually simple. Since it's already represented as a vector, changing the numerical values is, in itself, the generation process. Of course, you need to consider various probabilistic factors. So then we can move directly to the predictive model. For 1D, the 1D table becomes the input, and ultimately, we again predict whether it's static or dynamic. But another thing we often do in 1D, although it's also possible in 3D and 2D, is multi-fidelity. Most of you don't have a lot of high-fidelity data. The results from actual tests are very expensive, and the quantity is small. So we usually use low-fidelity data, like CAE data or 1D data, and utilize it effectively to make predictions. And that's the process. Once a prediction is made, 1D optimization is, of course, straightforward. You can just use the conventional 1D optimizer that we've always used. And then you can reconstruct it in 3D. So as a case study, we had an instance where we predicted the performance of a ship engine. Test data for a ship engine is very expensive, so we used a 1D simulation instead. We gathered data for various edge cases from the simulation, trained both low and high fidelity machine learning models, and then combined them to achieve better predictive performance. That was the case study. So, looking at this, you can see that depending on the type of data we have, whether it's 3D, 2D, or 1D, we can divide our work into key scenarios. These are 3D prediction, 3D generation, 3D optimization, 2D prediction, 2D generation, 2D optimization, and 1D prediction, 1D optimization. And the detailed scenarios, as I mentioned earlier, depend on what we're trying to do. Are we trying to predict a scalar or a field or a transient state? Are we just doing generation or conditional generation, or generating an assembly instead of a part? And are we doing iterative optimization or generative optimization? Many different combinations are possible. Going further, let's say I want to improve predictive performance, then I can use multi-fidelity prediction. Also, if it's not just about the prediction itself, but I want to know how much I can trust it, I can predict the uncertainty. And of course, since data is often insufficient, we can also use predictions that leverage physical knowledge. So all these different combinations are possible. In a way, we've created a large menu of options. So over the years, we've solved about 70 different problems, and they all roughly fit into this menu. So we've been solving a wide variety of problems like these. Typically, since automobiles have so many components and systems, and then there are electrical and electronics, power components, ships, robots, and recently, even small modular reactors, yes, our applications have expanded to these areas. So we may know how to solve these problems, but how can engineers in the field easily apply these methods? Ultimately, what I wanted to do was create a tool So we created a tool called AslanX. You can think of AslanX as a tool that allows experts in the field, like all of you, to easily train and deploy AI models. It's designed to seamlessly incorporate all of those scenarios. So what does the user, the engineer, need to understand? They just need to understand this process, this flow. You import the data, and the tool automatically pre-processes it for the AI. Then you just define what the input and output are, the X and Y, and you just have to select which model to train. After it's built, you test it. And since other engineers will need to use the model you've created, you can then deploy it. These functions aren't performed through coding, but rather in a workflow format. Everything is done through a GUI. It's a format where you just need to change the values. So let me show you a quick Let me show you the screen. You can train and pre-process 3D data like this, select a model, and generate. You can also deploy the generated model as an API. The deployed model can then be wrapped into an app. You can import this analysis data, pre-process it, and then immediately predict the analysis results. You can immediately perform optimal design on the 3D results, and it handles 2D problems and 1D problems. So all the scenarios I mentioned earlier are implemented in this workflow format, making it understandable for engineers. All right, so now actually, what I want to discuss today is the final topic. We've worked hard on generative AI up to this point, but looking ahead, as we move toward autonomous design, what should we be thinking about? And what preparations do we need to make? I've been giving this a lot of thought myself. So first, let's start with the terminology. I get confused myself. AI, agent, agentic AI. It seems there are slight differences in definition depending on who you ask. It's like back when the term Fourth Industrial Revolution first appeared and everyone was asking, what exactly is the Fourth Industrial Revolution? However, the one thing that is certain is that as we progress from AI to agentic AI, the autonomy of the AI increases. This is a concept that everyone generally agrees on. So whereas conventional AI was a simple form where we provide an input to get an output, an AI agent, on the other hand, can select tools on its own and utilize them to solve problems. Then, when these AI agents gather and begin to collaborate, we call it a multi-agent system, which can solve more complex problems. And when autonomy is maximized to an extreme degree within that system, it's often called agentic AI. So in any case, the key aspects of this progression are autonomy, the ability to use external tools, and the capacity for collaboration. I think you can understand it in those terms. And from an engineering designer's perspective, I've also, long been involved in component design, then system design, and then designing systems of systems. In a way, the direction of this development seems quite similar. So how is academia changing in response? Well, in academia, various new concepts are being rapidly introduced. The term autonomous design has started to emerge. And in most cases, what's being done is, after diagramming the design processes that humans have traditionally followed, they try to replace each of the human actions with an agent. They're essentially swapping out the parts that can be automated. If you do that, it becomes a multi-agent system. Just like people collaborating, agents collaborate to perform the design. So does this only apply to engineering design? No. In fact, if you think more broadly, it can include R&D, and even more broadly, it can include science. So if you look at recent studies using these multi-agent systems, a key characteristic is that they first utilize ontology. They organize past data, create a knowledge graph from it, and then utilize the relationships between different data points. And when creating this agentic system, they always include a critic, an agent that performs evaluations. So whereas in the past, AI was something that would start and finish in one shot, now it evaluates and keeps iterating to see if it's right or wrong. So I took another look at these two perspectives, generative design and autonomous design. Oh, time is flying. First, from the generative design perspective, as I mentioned, the human is still the decision maker, and the focus was on what? I was like that too. What should we make? What should we generate? But now with autonomous design, how to make it has become more important. Because even to make the same thing, there are so many different processes and methods. How to collaborate to solve the problem. So how is becoming important. So in generative design, we kept looking at the design results, but now in autonomous design, we need to look at the design process. And now instead of generating in one shot, it's about iteratively making, critiquing, until the problem is solved. And in the past, it was okay for it to be a black box because it just had to provide a solution. And since I was the decision maker, it was fine. But as we move toward autonomous design, if we're going to let the AI make decisions on its own, the results must be explainable. It made something well, but if you don't know how and why it was made this way, you can't trust and use it, right? Right? As long as we entrust decision making to AI, it must be explainable. And we should no longer look at it at the component level, but at the system level. It shouldn't be done in a siloed state, but in a networked state, linked with all other tools and systems. Finally, the difference between human in the loop and human on the loop is that with human in the loop, the human participates, but as a participant, as a member of sorts. But with human on the loop, they are more detached, acting only as an observer, just as a supervisor. So the level of the human's role changes. So even so, we are going in this direction, but we need to take a first step, right? So what we're trying to do first is, okay, since the process is important, what if the AI could find an optimal workflow on its own? So a process can ultimately be represented as a workflow, and having various workflows essentially means conducting various experiments. So in the past, we would solve problems by having a human make small incremental changes within a specific predefined scenario, like the one we just laid out. But now, since there are so many different ways to solve a problem, what if an agent could create these various workflows on its own and find the most optimal path? You know, if you've seen the Avengers, when Doctor Strange is trying to defeat Thanos in the end, he considers countless combinations, right? He explores an enormous number of ways the many heroes could collaborate and fight to defeat the enemy, and then finally finds the one way. In a sense, it's that kind of concept. So the direction we're heading in is toward this kind of autonomous design platform. So through ontology, we can effectively incorporate and utilize the design know-how from problems we've solved in the past, allowing the AI to autonomously create the best workflow to solve a given user's problem. In other words, it's about finding the how. And by integrating well with existing high-quality commercial tools, we aim to create an AI solution that can ultimately evolve on its own. This is my last slide. So are we just talking about this? No, we've already started development. So now, when I input what problem I want to solve, it autonomously creates a workflow based on past information. It's not a human creating it. It suggests, I can solve the problem this way. The great thing about creating a workflow like this is that a human can understand it. You can see, this is the process it used to solve the problem. Then you can also review those processes. So next year, you'll be able to see our upgraded product. To wrap up. So earlier, I explained why Korea needs product development AX now, and I shared my humble thoughts on how the future of engineering design might evolve. Of course, I don't actually know. How could I possibly know the future? So as you well know, the best way to predict the future is to create it. So I believe that Korea, which is already strong in manufacturing and recently became the country with the third most GPUs in the world, has the potential. So in this field of design, rather than just predicting the future, I hope that we can all create the future together. Yes, thank you.